all of this yellow is going to kind of spread north.
Heading into early next week. Particularly disturbed spell of weather is on the way with widespread downpours.
Take your umbrella.
Man, I hope it doesn't rain in 634 days. That's my cousin's wedding day, and a big pour would really ruin the mood. It's quite the institution these days, weather forecasting. On the day-to-day, it's essential. We plan our days or wrap ourselves in plastic and hope for the best. We pretty much take it for granted, right? We're sort of past the I can feel it in my bones weather prediction of the Old West. But now, weather predictions take up the lion's share of computing power in the world. One weather station alone in the US uses 8.4 petaflops, which is over 10,000 times more powerful than the computer this script was written on. These tools are getting stronger and stronger, so theoretically, we should be able to predict much further into the future. This is when we run into the hardest of hardcore impediments to weather prediction. But for posterity's sake, let's ask the question, why is it so darn difficult to predict the weather, and what are the limits we're facing?
First, we go to Ryan Marshall, who's out monitoring the snowfall. Ryan, what's it look like out there?
Yeah, it looks like snow, just like I predicted in my forecast from the studio.
In the 1800s, meteorologist Robert Fitzroy began publishing his weather forecasts in the Times. They predicted weather through observational data and then compared that to old weather charts showing similar patterns. He was off the mark, to say the least. Now we have the ability to simulate many different possibilities for the weather and have wised up to the fact that previous trends are not a surefire way to predict the weather in the future. Our main method of predicting the weather is through Doppler radars, which use the Doppler shift, surprise, to study the velocity and direction clouds are moving in. It sends out a bunch of signals and then waits for them to return. Now, you probably know the Doppler shift from a siren. When a police car blazes past with the siren blaring, the pitch will change as it passes you, because when the object is moving toward you, the frequency compresses, and the opposite happens when it moves away from you. Meteorologists use this phenomena to identify not only what direction clouds are moving in, but also what they are precipitating. The other main method we use is satellite imagery. Of course! What better way to glean some information about our world than using the 5,774 objects we've shot into space since 1957? Well, we'll have to keep shooting them off because only around half of those satellites in orbit are still operational. So long, Sputnik. Forecasting is a simulation. We make predictions based on current data, so the more data we have, the clearer the picture. If we think of the bits of data as pixels, then the more satellites we have, the higher the resolution we get of the current weather patterns. When I say satellite, I don't mean we just shoot a couple up there and they'll tell us the weather. We have 3 different types, with 3 distinct jobs. The first one follows specific points on Earth to follow the weather immediately. Then the second one orbits between the poles of the planet for a more comprehensive view. This last one monitors crazy solar patterns, essentially warning us of when the next disaster blockbuster is going to play out, but this time for real.
No, Daddy! Hang on, baby, hang on!
So it seems pretty solid, right? We've got a bunch of satellites, some radars, and they give us a pretty comprehensive view of the planet. But this only gets us so far. In order to be perfectly accurate, we have to account for every single variable. Wind speed, wind direction, humidity, air pressure, temperature, density, time of the year, the tides, pollutions, allergies, which planets are in retrograde, your moon sign, which side of the bed you got up on. The possibilities are endless. So we should embrace the chaos! That's right. Weather is a chaotic system. As metal as it may sound, the term means that tiny changes in initial conditions can have drastic effects in the later outcome. Kind of like, if a butterfly flaps its wings on the one side of the Earth, a hurricane might occur on the other. Take a pendulum. We can easily predict the pattern it will make. But look at a double pendulum. It's much more difficult. But we can definitely figure that one out through simulations. But if we add more, say 100, then it gets way more difficult. Say that each double pendulum is a molecule in the atmosphere. Then we would have to account for 2 × 10⁴ of those pendulums. That's 200 tredecillion of those pendulums. In order to account for chaos, we use chaos theory, which is the study of systems which appear stable in the short term, but cannot be accurately predicted in the long term. So after coining the term butterfly effect, Edward Lorenz, a meteorologist at MIT, created an even more badass sounding term of the chaos theory, specifically for weather predictions. In order to study this, he created a system that alters initial conditions and then shows their short-term effects frame by frame. With this system, he was able to more or less prove the butterfly effect. But the accuracy diminished after about 2 weeks, so Lorenz set the theoretical limit for our ability to predict the weather. We still hold this limit today, because anything beyond 14 days is just too chaotic. So basically what chaos tells us is that the weather is not a wholly stable system. While there may be some patterns present, that doesn't mean the future will reliably follow this pattern. Edward Lorenz described chaos like this: when the present determines the future, but the approximate present does not approximately determine the future. Therefore, weather cannot be predicted very accurately based on past data, so we use simulations of chaotic systems in order to mitigate this uncertainty. For instance, using advanced AI and even more computing power, meteorologists can run more and more systems with variations in those initial conditions, and then combine them to make more educated guesses as to the most likely weather conditions. All of these different elements are then combined in what's called ensemble forecasting, usually for hurricanes, where its different possible paths will be modeled and averaged together.
Now, there's still models that bring this far way out west towards Mobile, Pensacola. There's models that have it way east of the Bahamas. This is just kind of the general consensus.
But think about it. Even if we're using the averages, that doesn't assure that one of the extremes will not happen. We're playing with chances here. There's still no certainty. If you think about it, meteorology is essentially predicting the future through simulation.
Hedlund had some pretty convincing data. They've asked me to feed it into my paleoclimate model to track the next set of events.
So it's insane to consider that we can accurately predict the weather next week, when I have no idea what socks I'll be wearing tomorrow. So even though that wedding of my cousin is fast approaching, maybe I'll take a rain check. I mean, there are just too many variables to take into account. We could all keep to very strict routines so we don't add more variables to that list, or maybe we could just embrace the chaos. Thanks for watching. You can find all the research we use down below. Like and subscribe, and I'll see you next week.